I want to share my screen with you for the moment. And many of you would have seen this, but we've got quite a number of new people on board today. So what I want to say to you is, first of all, a huge welcome from Cement and Concrete SA to this concrete fix. Our partner members are AfriSam, Lafarge, PPC, and Sepako Cement. And then we've got many more members. Our gold members, SEMSA and CRESO. Our silver members, Chioli, Kostra, Quick Group, Seeker. Our bronze members, and I'm going to let the screen just go so you can look at all the logos there. More bronze members, and some of them are new, the first time that they're joining us today. More bronze members. We've got an emerging contractor member of whom we're very proud in the Eastern Cape Glow Queue. Our associate members. Our academic members. And then, of course, to all you, the individual members, it is lovely for us to have so many of you on board today. And if you're not a member of Cement and Concrete SA yet, please remember to join. It is certainly worth your while, and I believe that you're going to get lots of added value from being a member of Cement and Concrete SA. A wealth of information is available on our website. The web address is on your screen at the moment. We're also on Instagram and on LinkedIn. Please keep your ears open, your eyes open for announcements, and have a look at the website. I think you may be surprised at what is available. The website has been redesigned and it contains much more than it did last year. Concrete Baton, the March issue is still available on our website, can be read online. And the good news is that the June, which will be available after the Fulton Awards, will be both a print and online issue. So you as members will be receiving your print copy in the post, but it would also be available online. So we're looking forward to that one. Remember Fulton's Concrete Technology, the 10th edition, the handbook is available for sale. And as you may know by now, that today's talk, Rod Rankine's talk, is based on the chapter that is written in Fulton's Concrete Technology on cracking, but he's not going to deal with the chapter. He's just going to give an outline of some of the problems to do with cracking. So you'll have to buy the book to get the full picture. Our School of Concrete Technology, professional online and classroom-based engineer education. So please get in touch with them if you want to discuss and see where you can fit into any of these courses or how these courses can help you achieve your goals. All our Concrete Fix events carry CPD accreditation. And if you wish to get your CPD points, make sure that you've RSVP'd to Natasha with your registration number so that she can load you when the points become available. A couple of forthcoming events, the bowl splits in the Western Cape, next Thursday, the 26th of May. You would have seen it on LinkedIn, you would have seen it on Instagram, and if you remember, you would have had the notice about that. If you haven't booked your place already, please do so. And then the Fulton Awards poster competition. That is online. This is a fun way of getting to know the 24 entries in the Fulton Awards. And there's a prize to be won for the correct entry drawn on the night. That competition is sponsored by Kostra. So please go online to our website and enter the Fulton Awards poster competition online. And then I think what remains to be said is we are building a future together. Please become part of the Cement and Concrete SA fraternity. But what I want to say specifically about today, thank you to CRESO, who's sponsoring all our concrete fixes. And I actually want to show you a video from CRESO. So let me share my screen so we can watch the video. Thank you, Carmelisha, and everybody from CRESO for making this possible. And thank you. Thanks again to CRISO for sponsoring this series. Now, Rod, if you want to start getting ready to share, I'm about to introduce our speaker for the day. For many of us, Rod Rankine does not actually need introduction, but there may be some people who've not met him before. Dr. Roderick Rankine is a registered professional engineer and concrete technologist. His company, Rod Rankine Engineering Solutions, CC, conducts forensic investigations on failures and assists in the development of construction specifications and solutions. May I just ask that you will mute your microphone if you're not speaking? Please all mute your microphone if you're not speaking. He's also certified level 2 infrared thermographer. Rob is currently a committee member of the SAICI Environmental Engineering Division. He's developed various technologies, including a plate dowel and installation machine for retrofitting the edges of industrial floor slabs for load transfer called the retro dowel system. He is an author and co-author of more than 40 papers published in accredited journals of science and engineering, international conference proceedings, and books. And for those of you who saw Rod in the beginning and saw his background, he's actually sitting in his personal library. It is a library second to none. So, Rod, you've got my thumbs up for being informed and being the best person to talk to us about cracks in concrete. Thank you. Please go ahead.
Thank you, Hanley. First of all, can everybody hear and can you see the presentation?
Yes, thank you, Rod.
Is that all good?
Yes, thank you.
The presentation visible. Okay,
yes,
then I must just figure out how to get to the next slide. I think I pressed the down arrow. Right, so the title is Cracks in Concrete, and it's quite a long subject. So I've just highlighted, I'm going to highlight a few of the most common cracks, the ones that are most easily dealt with. And there's a list of them. I'm going to talk about the plastic cracks, which have been classified as non-structural cracks by the British Concrete, the British Concrete Society. They have a publication called Non-Structural Cracks in Concrete. I'm going to show you an interesting case study where it so happens that one of those cracks, a plastic settlement crack, had a structural aspect to it. It caused a failure. And then I'll spend some time on drying shrinkage cracking and also cracks caused by corrosion of reinforcement steel, because that's quite an important cause of cracking. And what I want to say at the outset is that it's easy from an academic point of view to classify cracks into these categories. But very often when you go and diagnose a cracked structure in practice, you'll find that there's a combination of factors which result in a crack being what it is. So very often that starts off with a plastic settlement crack, which becomes wider because of plastic shrinkage. And then as the concrete hardens and dries out, it becomes even wider still due to drying shrinkage. And it can become a lot longer and a lot wider because of drying shrinkage. So in the real world, it's a little less easy to categorize these cracks. It's not going to the next slide.
Could I suggest that you just click on the presentation icon? It's just to the left of the size, the percentage bar there.
Let's just have a look if I can see the presentation icon.
Sorry, Rod, if you can just go back to the previous slide, just for a moment.
Yes. There, can you see the previous slide?
Okay.
Yes, thank you.
Can I go forward?
Yes, thank you, Rod.
I'm just
And
trying
Rod,
to.
if you look where in the toolbar where it says comments, if you go click on the icon, that's 4 positions to the right of the comments.
Yeah, I'm trying to get there, but the toolbar from the Zoom is getting in the way.
Okay.
Rod, click on the toolbar from Zoom. That should take it away. And then you should see your full screen so you can get to the presentation mode.
It just keeps coming back, Hanley.
Okay.
Presentation. Can I stop sharing for a moment?
Yes, sure.
Is that any better?
Rod, at the moment, you're not sharing. We can't see your screen.
Okay, I'll go back and share.
And Rod, we had a comment that F5 is the shortcut to start the slideshow. So the moment you start sharing, try F5, but you're
Right,
still
I'm
not
pressing
sharing.
F5.
Okay, but you're still not sharing at the moment, Rod.
Yes, I've got to get back to the share screen. I've lost that share menu altogether now.
Rod, just click at the bottom or at the top of your screen so you get that menu back.
Please look at this. Oh, yeah.
Hello, can you?
Rod, if you click anywhere on your screen, you should get the bar back where you could start sharing screen.
Or if you move your mouse anyway on the screen.
Right
Usually
there, I've got it. Let's come back.
there we go.
Can you see it?
No, if you
no, mate.
click on share screen.
Share.
Okay, now it says you've started screening. Now try F5, Rod.
I'm pressing F5.
Okay, Rod, at the bottom of your screen where your cursor is at the moment, 3 spaces to the right should be the presentation mode. Just your cursor, just go up to the black line, just above that, or yeah.
There, Hanley.
A little bit higher, and a little bit to the
screen.
and a little bit to the down again, Rod.
Yes.
In the black line at the bottom, you see notes, comments.
No, I don't see notes or comments.
Okay. Can anybody else assist Rod there?
Rod, if you can see your top, toolbar, just click on slideshow and start slideshow. Click on slideshow. There we go.
Okay,
Yeah.
I've clicked on it.
Okay,
Double click.
Okay, from beginning. Click on from beginning. Go to the left, go to your left from beginning.
Left.
There you go.
Yeah, click.
Yeah.
Okay, what can you see now?
Okay, Rod, there's obviously some setting in your presentation, but I think you can carry on. We can at least see the presentation. So you can start with your, yes, let's do it that way.
Okay, so there's a schematic diagram that shows the cracks in their purest form, as you would classify them. As I said, in reality, they often a combination of different factors that result in the crack's final proportions and shape.
You're at the left.
All right, so the first type of crack here is we're looking at plastic settlement cracking in columns. So this is an elevation of a column, and it's sort of near the middle of the column, I suppose. And what causes these cracks is the fact that the solid ingredients in concrete, that's namely the stone aggregate, the sand, and the cement particles, have a relative density which is greater than water. So if you imagined a bucket of water into which you threw handfuls of sandstone and cement, where would the solid particles go? They'd settle to the bottom of the bucket. And the same thing happens when you mix up an homogeneous mixture of concrete and you place it and you compact it. The solid particles start settling downwards. They're pulled on by gravity. And the rate of settlement depends on the size of the particles. The bigger particles tend to settle faster than the smaller particles because of a phenomenon known as Stokes' law. It's got nothing to do with the density. It has everything to do with the ratio of the volume to the surface area. So very small particles have a low volume and a big surface area, so that they're more inhibited from settling by drag. But if you think about it, the amount of settlement, the potential for settlement, is greatest at the top of the wall or the column and least at the bottom. So what you'll see here are cracks which correspond to the levels of the stirrups or the hoops, the horizontal reinforcing that holds the axial compression bars of the columns together. And to understand how it happens, imagine you were a particle of stone and you were sitting, I don't know if you can see the cursor here, if you were sitting just beneath a reinforcement bar, which is, remember, fixed in space, there's nothing to stop you settling other than the drag, the resistance of the fluid. But if you were a particle of stone sitting directly on top of the reinforcing bar, that reinforcing bar would support you and you wouldn't be able to settle. So what happens is that you get sagging or settling of the concrete beneath the reinforcing and support by the reinforcing stirrup of the concrete immediately above that stirrup. And you get a discontinuity or a crack forming in the plastic state. That's while the concrete is still fresh and plastic. And bleed water, which rises up because it's got to make room for these settling solid particles. It's the lightest ingredient, so it rises to the surface. It occupies the space in these cracks. And then some weeks later, you strip off the shutter and the water evaporates from those cracks, and you see these ugly cracks left behind. And the cracks tend to be smallest, narrowest near the bottom of the column or the wall, and widest near the top. And that's purely because the relative propensity for settlement is much greater at the top of a column than the bottom of a column. And if you test concrete for durability and durability properties, you tend to get much better results if you draw cores from the bottom of the concrete than you will from the top of the concrete, because there's much more water near the top, and you get more of these cracks near the top. And here's a picture of a core. It's the same core front and back, where you can see what we call bleed water discontinuities beneath the horizontal surfaces of aggregate, of coarse aggregate. And here you can see some more bleed water discontinuities. And these are caused by the bleed water being trapped beneath these horizontal surfaces. And here you can see some more alarming ones on a column. These are very typical. And they also occur on horizontal surfaces. So this is a surface bed. In fact, this is a raft foundation. And what you see here is the cracks form a regular geometric pattern, which corresponds exactly with the reinforcing mesh that was used here. These are sort of 200 millimeter by 200 millimeter cracks. So what happens in the case of a slab is that the reinforcing provides a restraint on the settling aggregates and particles. And the only way that these aggregate solid particles can move around the reinforcing bar is if they move laterally. So they've got to move sideways before they can move vertically downwards. And as a result of that sideways movement, the concrete effectively breaks its back over the reinforcing steel, which is fixed in space. And if you have a look at a very acute angle, there's a straight edge over here, you'll see a gap forming between the bottom of the straight edge and the middle of that span. So the highest points on the concrete are directly above the bars, because the bars are supporting the concrete and restraining settlement. But in the middle, the concrete's free to settle. So the million-dollar question at the bottom here, if this was your job and there was a risk that your company wasn't going to be paid because of these uncycled cracks, what would you do? And it's difficult to ask the audience for an answer here, but I'll just put you out of your misery and tell you. The thing that you would do is revibrate the concrete. You'd put your poker vibrator in half an hour or an hour after you've initially vibrated it, and you stir it up. And you can't prevent these cracks forming, but once they're formed like this and the concrete's still plastic, you can eliminate them. So by putting your vibrator back here and vibrating the surface, you shake off those stones which are precariously supported by the rigid reinforcing bar. You shake them to the left and the right, and it flattens the surface and it knits the concrete together. It knits those cracks back together. It's as simple as that. And one must bear in mind that after you've revibrated, settlement will continue again. So you've got to keep on revibrating the concrete until such time as the concrete goes hard. And people often say, but won't we over-vibrate the concrete? And the answer is no, you won't. I've proven it. If the mix has been properly proportioned and well designed, all that will happen is you might get a little bit more stone near the bottom, but you won't have any cracks. It's far better to vibrate the concrete more than you need than to under-vibrate it and to risk all the problems that come with under-vibration. Now, the same mechanism occurs where you've got a tie bolt hole. So this is a tie bolt hole in the shutter. And exactly the same thing happens. The concrete above the tie bolt is supported and restricted from free settlement, but the concrete underneath the tie bolt is free to settle. And again, the remedy for these cracks is exactly the same. Just revibrate the concrete. And on a shutter, it even helps to just take a rubber mallet and to thump the face of the shutter. And that stirs up the concrete near the surface and it eliminates those cracks. And it's really worth doing that because clients get quite upset. In that first picture I showed you of the raft foundation, the contractor didn't get paid for that. And he had to cast a new slab on top at his own expense, despite the fact that several engineers, including myself, went to site and assured the client that these were non-structural cracks. And if he was going to put a screed on top of them, there was nothing to worry about. They were dead cracks. They'd be very unlikely to reflect through the screed. The client insisted, and that caused the contractor a big loss. And here's something interesting. This is a coffer slab. And what happened here was they overdosed a lignosulfonate-rich admixture. And the concrete didn't set for several days. Now, if the concrete remains plastic, it continues to bleed and it continues to settle. And if it remains plastic for a prolonged period of time, the plastic settlement cracks just become larger. They become longer and wider and more unsightly. So if you ever have a situation like this and the concrete's not setting because it's very cold or it was overdosed with a retarder or a lignosulfonate admixture, the thing to remember to do is to put the poker vibrator back every few hours and give it a stir. Won't affect the hydration, won't affect the setting much. It's worth doing to eliminate these unsightly cracks. Now, this is an interesting case study. This is the one I told you about where these so-called non-structural cracks became critical and structural. This was a parkade in Bank City with a coffer slab, and the coffer slab was only 75 millimeters thick. And in the middle of this coffer slab was a light mesh, a light steel mesh, right in the middle of the 75 millimeter thick section, a 200 by 200 mesh. And it just so happened that the dimensions of the mesh, 200 by 200, coincided almost exactly with the footprint of a motorcar tire. So when a motorcar drove over this, the full weight of the motorcar was borne by this little area of concrete which had cracked with plastic settlement cracks right above the mesh. So here's a little schematic, and you can see there's the mesh, there's another piece of mesh, there's the motorcar wheel, and the plastic settlement crack has caused a discontinuity between the top of the steel and the top of the slab on all around the perimeter of the square mesh. And so it's effectively reduced the effective depth to resist punching shear. So all that was necessary was for a little area to punch out, which was about 35 millimeters deep. And there you can see the result of the punching. They had put a plate of mirror steel on top facing downwards. So you could see the reflection of the tape measure and the mesh here. But what's quite interesting to see is how the perimeter of the piece of concrete that fell out is defined by the mesh, the 200 by 200 mesh. And what we also found investigating is there was some plastic electrical conduit stuck in, and it was fastened to the mesh. So that made the situation even worse. But fortunately, it was restricted to just some local areas. So the other type of plastic cracking is called plastic shrinkage cracking. And this is cracking caused by a reduction in the volume of the concrete caused by evaporation or absorption of water. So in this slide here, you can see loss of water by evaporation at the top and loss of water by absorption at the bottom. And remember that as the rule of thumb is that in concrete, you have about 20% volume of water. And with admixtures today, we get that down to about 17%. But if there's any loss of water, only two things can happen. There's either a complete reduction in the volume of the concrete, or it leaves voids behind in the concrete. And it's due to the reduction in volume that we get these cracks. So you'll see the mouth of this crack here is widest at the top. So this crack was caused by evaporation of water from the top. But we sometimes also get cracks with wide mouths at the bottom if we cast the concrete against a porous and permeable substance like soil. If we're casting a concrete surface bed against compacted earth, you'll see crack the opposite way. Can people still hear? I hear some talking in the background. Are we all good?
Yes, thanks, Rob. I've just muted some people. Please make sure that you mute it. Thank you.
So the mechanism that causes these cracks is the same mechanism that causes the clay in a riverbed to dry up and crack like this. Only you'll never see cracks quite this wide in concrete. I haven't in my career. But the reason that I haven't is because clay contains a much bigger volume fraction of water than does concrete. So this clay probably contained like 70 or 80% of water when it was laid down. And remember that when it shrinks, it's going to shrink vertically and horizontally. So these cracks tend to happen after the capacity for vertical shrinkage has greatly diminished. So when the clay is sort of stiffened enough that it's not going to collapse vertically anymore, then it starts to dry out and you get the horizontal shrinkage. And it's the horizontal shrinkage which causes these cracks. And it's the same in concrete. It's the same mechanism. And the patterns that you get are very much dependent on the conditions at the time of placing the concrete. So this note just really says that if there's no restraint, there's no cracking. And it's very prominent in the interior of the concrete, very, very prominent on the high felt between the months of the beginning of August and the end of October, because this is the driest part of the season. And when you're placing concrete under conditions which are hot, going up to 30 degrees, and sunny and windy, where the relative humidity is high, then you get the maximum rate of bleeding. Sorry, the maximum rate of evaporation of your bleed water. So when the rate of evaporation of water exceeds the rate of bleeding and the concrete surface becomes dry, that's when you're most at risk of these cracks. And there's times of the year in Johannesburg where the weather's so non-conducive to placing concrete that I advise people not to place concrete. If you've got 20 kilometer per hour wind on a 30-degree October day when the relative humidity during the day drops less than 10%, don't even try to place concrete. To some degree, the presence of bleed water is a godsend because it's sacrificial. While there's a layer of bleed water on the surface, this can't happen from evaporation. It's once the bleed water starts evaporating and it disappears that the surface dries out very quickly. And the presence of admixtures or additives that inhibit bleeding, something like silica fume, microsilica, would exacerbate this sort of problem. So never ever put silica fume in a slab which you're going to cast outdoors. Not a good idea. So this next picture shows the sort of crack pattern that you might expect to get if you were casting concrete outdoors. And the cracks tend to align themselves at about 300 to 500 millimeter centers. They can be anywhere from half a meter long or 300 millimeters long to a couple of meters long. And the cracks tend to form perpendicular to the prevailing wind. So in this case, the prevailing wind might have come from this corner inwards, or it might have come from this corner of the photograph. It would be a wind sort of horizontal to this photograph in this instance. And this is the type of crack pattern that you might expect to get if you were casting indoors or on a day when it was very still. So those cracks tend to be more randomly orientated, and they tend to resemble rivers on a map. Now, another characteristic of these cracks, these plastic shrinkage cracks, is they never terminate at the edge of a slab. They tend to terminate short of the edge of the slab. And it's an interesting thought experiment to think why that is the case. And I'll tell you as well. The reason is because the edge of the slab is free to contract inwards. The concrete can pull away from the shutter quite easily. And if it can do that, it retains its, it doesn't retain its, it loses its volume without forming a discontinuity. It's able to shrink without forming a discontinuity. Once again, the million-dollar question is, we don't want these cracks on our site. What do we do to prevent these cracks ever happening? And there are two things you can do. If you are casting concrete on consolidated earth, such as a surface bed or a foundation, what you do, people always say, put plastic down, and yes, that would work, but that's expensive. A much more cost-effective solution is to take a hose pipe and to pre-wet the soil, pre-wet it the night before, and if necessary, give it a mist spray on the morning that you cast the concrete. So that's the first thing you can do. That would prevent excessive loss of water by absorption into the soil. And the second thing you can do is to cover your concrete while you're placing it and compacting it sometimes if the weather's bad. And certainly when you've finished placing and compacting the concrete, just cover it with plastic, weight the plastic down around the entire perimeter with bricks to prevent any air tunnel effect, and leave it so that it doesn't dry out prematurely. And this is just a picture of a core which shows how deep these plastic shrinkage cracks can go. If you get some severe plastic shrinkage, and if you get some absorption from the soil below, yes, it can go all the way through. I've even seen suspended slabs where they go all the way through. You take a bucket of water or a watering can and you sprinkle it up on the top of the slab, and you run down and you watch it leaking out of the soffit. So they can go all the way through. Now, we get exactly the same phenomenon happening in plaster, and it's even more severe in plaster in some ways, particularly if we're plastering burnt clay bricks. So you get this typical pattern, I call it polygonal pattern of cracking. I was once traveling to Bloemfontein on business at about 2 o'clock in the afternoon. I stopped at the Ultra City outside Bloemfontein, and they were plastering a west-facing wall in January on a baking hot summer's afternoon, and they hadn't pre-wet the clay bricks. And I kid you not, but as the plasterer took his trowel and he applied the plaster, you could see the cracks opening up just behind where the trowel had gone. It was literally, these cracks happened in a couple of seconds of plastering. And here's some more, very typical. And with time, these become bigger because of drying shrinkage. But there's another phenomenon. The plaster, because it contains Portland cement, it shrinks over time. It has an overall tendency to shrink over time. But the burnt clay bricks have an overall tendency to expand over time due to what we call the irreversible moisture expansion of brickwork. It's a phenomenon that occurs at the atomic lattice of the clay mineral. But take my word for it, over time, clay bricks tend to expand. So you can imagine that combination where you've joined these two materials together, which are moving on opposite directions. The cracks just get wider and wider over time. And a big problem occurs that owners complain that this is a defect and the builder must come and redo it at his expense. And they usually believe that because of the guarantees offered by the paint suppliers. Most suppliers of acrylic paints today offer a 10 or a 12-year guarantee on their paint. And if you call the paint manufacturer to come and have a look at this, he says, well, no, this is a defect in the plaster. It's the substrate which has failed. And our paint is only as good as the substrate, so we don't honor our guarantee. And the problem is that there's no acrylic paint in the universe which can accommodate this degree of movement. Just imagine a crack, a hairline polygonal plaster crack that starts off life at the time when you apply the paint. It might be 0.05 of a millimeter wide. It's a hairline crack. And you now put this acrylic paint on top, and because of irreversible expansion of the bricks and shrinkage of the plaster, it opens up to 0.1 of a millimeter. Now, the difference between 0.05 of a millimeter and 0.1 of a millimeter is 100%. Okay, you've asked, do you expect that paint to stretch 100%, to elongate, to double? An elastic band can do that just, and it perishes very quickly. Acrylic paint can't do that. And So builders get blamed for this sort of thing unfairly. There are some things that they can do to exacerbate the problem, but this can happen on any plaster. And one of the best ways to prevent this from being a problem for your owner is to reinforce the paint with fiberglass tissue. You impregnate the first coat of acrylic paint with fiberglass tissue, or you impregnate the fiberglass tissue with paint, and the fiberglass tissue bridges these cracks, and nobody ever worries about them ever again because you don't see the cracks. And this is just a photograph to show you just how much water a clay brick absorbs. So this is why it's so important to pre-soak burnt clay walls before you plaster them. Otherwise, can you imagine each brick sucking half a liter of water out of the plaster? The plaster doesn't stand a chance. It's going to shrink and crack, and it's not going to hydrate like it should. And what you find after some time is that the paint starts peeling and it flakes. And when it rains, the rainwater enters these cracks. And if you dig here with a spike or you rub with a wire brush, you'll find that the plaster is very, very soft adjacent to the cracks, but actually quite good in between the cracks. And this is because the rainwater running down the face of the wall enters the cracks and it dissolves the cement paste. Cement paste is water soluble, just like rainwater dissolves limestone and dolomite in caves, forming solution cavities. Rainwater also dissolves cement paste from inside the cracks. So the longer these are left untreated while the owner has a dispute with a contractor, the worse the situation becomes. And with acid rain, it's even more rapid because acidic water is far more aggressive to cement paste than just fresh, hard water, which rainwater is. It's always hard water because it's got very little dissolved minerals inside it. So it's hungry for whatever it can extract from the cement paste. And these cracks always look far worse after the rain. So that's a characteristic of cracks. And if you want to take a photograph of a crack, you very often are disappointed that when you develop the photograph, you can't see the crack. One of the ways to make it stand out is to sprinkle some water on it. And the water in the crack's the last thing to dry out. And then you take a picture when the surface is basically dry, but the crack's still wet. It's just a trick. And failing that, what I sometimes do is just draw with a piece of chalk to emphasize where the crack is. But then in your report, just acknowledge that you used chalk. Now here's an interesting picture. This is a picture of the schoolhouse. This is a replica of Herman Charles Bosman, the South African writer and poet's schoolhouse. He was a school teacher and he had a schoolhouse just outside of Gaborone. And the people of the Groot Mariko Herman Charles Bosman Society decided to build a replica of Herman Charles Bosman's schoolhouse in the Groot Mariko on the way out to Zeerust. And they used traditional materials to build the school. And so they used sun-dried bricks. I think the only time they used Portland cement was in the foundations. Otherwise, everything else is traditional. And they plastered this schoolhouse with a mixture of cow dung and clay. But right at the back of the schoolhouse, on the back wall, on the inside, they left about a square meter to show how the materials were applied. And you can see the sun-dried bricks here. And then on this little portion here, they left the cow dung out. And look how it has cracked. Very, very big. These are plastic shrinkage cracks. Compare the size of the cracks here. Well, you can't see them at all. There's no visible cracking where the cow dung was. And what's magic about the cow dung is it contains undigested cellulose fiber from the cow's digestive tract. The cow cannot digest the cellulose fiber. So those fibers form fiber reinforcement for the plaster. And in the medieval times, medieval years in Europe, they did something similar. They would take horsehair from when they brushed their horse, and they would mix that with the plaster, and these plastic shrinkage cracks would disappear. Nowadays, you can buy polyester or polypropylene fibers. I don't mind which ones you get. Polyester is attacked by high alkalis, but it really doesn't matter, because by the time the polyester is attacked, the fibers are redundant. They've done their job. They've distributed the forces which caused the cracking and thereby prevented any visible cracks. So it's something I would recommend you consider if you want to combat the problem of cracking in plaster. This is called crazing, which is really just a surface phenomenon. It's got no structural significance whatsoever. You sometimes get this in a surface which has been overworked or overtrailed. And then we've got the drying shrinkage cracks. Now, these are due to the shrinkage which happens after the concrete is hardened, as opposed to the plastic cracks which occur before the concrete hardens. And the reason that we saw cut industrial floors is to enable drying shrinkage to take place freely by the cracks opening. And what you notice here, you may be able to see the chalk lines that I've emphasized. The cracks tend to emanate from re-entrant corners. A re-entrant corner causes a stress concentration, and that's where you're likely to have a crack. And what is very typical about drying shrinkage cracks is that they tend to run from edge to edge. They tend to bisect a slab. And if a slab is long and thin, it will bisect the slab transversely somewhere in the middle third, because that's where the stresses are the highest. And you'll see this piece of concrete, every corner here has a radial crack coming out. And this is due to the stress concentration caused by the re-entrant corner. And this is a phenomenon that occurs in all materials. In the Second World War, the Liberty ships built by the Americans for the Allies, most of them cracked up. They tried to make these ships very quickly and very cheaply, so the windows would cut out square. And in a high sea, the ship becomes a simply supported beam. It tends to have a lot of bending going through the hull, and you get a lot of fatigue at the same time. And what would typically happen is there would be a stress concentration at a very sharp right-angled corner of a window, and that would start running down the bulkhead, and it would run through the deck of the ship, and then it would go into the hull, and it would keep running until the ship broke in two. And it's overcome these days by people making the portholes and the windows and the doors oval. Instead of having sharp corners, which induce a lot of stress concentration, you round them off and you reinforce with extra steel all around these doors and windows, and then you don't get a crack forming. And the same thing caused the destruction of the de Havilland Comet, the very first passenger jet airplanes that were built in the late 1940s, early 1950s. Several of them fell out of the sky, and when the third one fell out of the sky, Winston Churchill made a famous speech, and he said that they would do an investigation, whatever the cost. No cost would be spared, and they would get to the root cause of the problem. So they took a de Havilland Comet, and they filled it with water. They put it in a water tank, and they filled it with water, and they pressurized it and depressurized it. And they simulated what would normally happen in pressurizing a fuselage of a jet that flies at high altitude, but only with water. And the beauty of water is that it doesn't develop as much strain energy. If you had done it with air, the whole fuselage would have exploded, and it would have been very difficult to pinpoint the root cause, the root source of the crack. But by filling it with water, they were able to pinpoint the source. And it was a window just behind the cockpit in the fuselage. It had a stress raising effect over here, and it caused the fuselage to split. But unfortunately, by that time, the de Havilland company had suffered so much financial trouble that it never really reestablished. Now, the same thing happens in concrete, but only you'll notice it doesn't really happen in concrete to have rounded edges. Okay, what you need to try and do in concrete is to eliminate all re-entrant corners as far as possible. And if you really do need them, you need to put lots of reinforcing here, and a lot of it must run perpendicular to the trajectory that you imagine the crack to come out of. And remember, the crack always tries to radiate at 45 degrees from that re-entrant corner. But first prize is not to have re-entrant corners. Concrete really doesn't like re-entrant corners. And the problem is that these cracks just run. Once a crack from a re-entrant corner starts, it runs, and as you see here, it can jump over saw cuts. And so this is the reason that we saw cut slabs, slabs on the ground, and we cut to a depth of about 1/4, and that induces a crack underneath. And it's quite important to note that where you do this, you mustn't have too much reinforcing steel. And there's a good argument for not having any, but there certainly mustn't be more than about 0.8% absolute maximum going through here, or the reinforcing will actually preclude the crack from opening. If the crack can't open, or if the crack can't form and it can't open, it cannot alleviate the drying shrinkage stress. And yet this is one of the most common mistakes we see in construction, is people put big reinforcing bars like this, running transverse across the crack. The reinforcing steel should be terminated. Certainly the heavy reinforcing steel should be terminated either side of the joint. And the problem is you've got to know exactly where your joints are going to be at the time that you lay your reinforcing steel, or you can't do that. So planning is critical, planning ahead. You can't just say, well, okay, let's think about where we're going to cut the joints tomorrow. That's too late. And what's one's also got to be careful of is not to bond brittle finishes such as floor tiles directly over a saw cut joint, like they've done here, or over any crack for that matter, which is live, because then we get what's called a reflection crack going through these brittle materials. And that's a cause of a lot of disputes in the construction industry. And then I'll talk a little bit about cracking due to corrosion of reinforcing steel. There's a bit of chemistry here, but I'm not going to go into the chemistry. There are two mechanisms. There's an inland mechanism that's primarily due to a loss of alkalinity caused by carbonation, and then there's the coastal mechanism that we get here due to chlorides. But the important thing to note is that when the corroding reinforcing steel rusts, the products of corrosion, the rust itself, which is a mixture of iron oxides and iron hydroxides, it occupies a significantly greater volume than the parent steel. And it's that increase in volume that causes the distress to the concrete initially. So there's the two mechanisms, and here you can see a graphic showing the volume of the parent iron, and then the volume of all the oxide and hydroxide derivatives of the parent iron. And you see this hydroxide actually goes up to just in excess of 6 times the original volume. And it's that expansion that causes the initial distress. And eventually, if you get sufficient cross-section of the steel lost, it'll lose its structural capacity and the structure falls down. But lots of trauma happens before then. Lots of disputes happen before then. So we need to do everything we can to prevent this mechanism of cracking and corrosion. And one of the things that you all know, I'm sure, is that one of the big causes of this cracking is where we don't have sufficient cover concrete over the rebar. This is a classic case of insufficient cover concrete. Often there's no cover concrete. But something that is not well known that I want to just emphasize is that the reinforcing steel is most vulnerable, and it starts corroding first adjacent to joints, to cold joints at lifts. What you're looking at here is the outer surface of a hyperbolic cooling tower of a power station. And notice how the steel's predominantly corroding first at these lifts. Now, these lifts of concrete, where you join concrete placed a few days ago with concrete placed today, that is the Achilles heel of all concrete structures. That's the worst concrete. That's the most inferior concrete. Remember I said the most inferior concrete is near the top of a lift because that's where the water migrates to. It's got the highest water cement ratio. And it's also the place where you've got a cold joint, and inevitably there will be cracks here because this concrete hardens before this concrete, and the two mixes don't knit together, and you get contamination of all sorts of things from dust to shutter oil to cigarette stompies. They accumulate at this lift, at this joint. And you need to be cognizant of that. You can specify the most durable concrete, but the reality is that's going to be inferior. And we need to think about how we find a permanent lasting solution to that problem. What we often find with severe corrosion is you get multiple planes of sheet delamination of cover concrete. So this is some concrete which has been affected by chlorides. And what you'll see is that you've got a freshly fractured face of concrete, which is more or less on the equators of the outermost mat of bars. And in some cases, it's fractured through the stone. But then there's another mat of steel, vertical steel bars deeper than that, and they form a second plane of failure along their equators. So you can imagine all these bars swelling in the same plane. The concrete between the bars goes into tension, and that has to be overcome. And it takes a lot of force, but expanding steel generates a lot of force. And then you get a whole plane spalling off. And there's a rule of thumb that not many structural engineers know, and it's not written into codes of practice, and that is that the closest rebar spacing allowed is no closer than 5 diameters. And when engineers, and there's a growing trend, they're doing this more and more, they pack the steel closer and closer, and it's very common today to find engineers placing steel bars at 3 diameters apart. So you'll see Y25s at 75 centers, for example, or Y32s at 100 centers. It's too close. You're going to get problems with sheets of concrete delaminating prematurely with only slight expansion of the reinforcing steel. And the best solution I know to this problem, and it's not widely adopted, is to hot dip galvanize the reinforcing steel. Now, I've been to so many concrete conferences in my life where this topic is debated ad nauseum. And people complain, I mean, they've been complaining for 50 years that the contractor can't get the cover right, and the 4 C's we always talk about. And we still have this problem, and we still try to address it in the same manner that we've always done before. Read the Riot Act to the contract. And it's a little bit like insanity. Albert Einstein's definition of insanity is doing the same thing again and again and again and expecting a different outcome. And that's really what we're doing in the construction industry. And if we just hot dip galvanize the reinforcing steel, we triple the life of the structure. It's a small premium to pay. You're going to nearly double the cost of the reinforcing steel. It's a small premium to pay in the greater scheme of things. And we're seeing some of it being done now on our national roads. This is a Sandroll Bridge near Wakkerstroom. And they've galvanized just these bars here that are closest to the surface, the shear bars and the stirrups and things. But my philosophy is you might as well galvanize it all. We have to stop building structures that fall to pieces. And since the 1970s, the quality of construction in our country just got worse and worse. And sometimes structures don't even survive a decade. I've quite frequently done reports on investigations and reports on structures which fell to pieces within a decade. We just cannot afford to build like that anymore. We've got to start building structures that last. We don't have infinite energy. We don't have infinite resources to waste. So we need to do it right the first time. And this is the best way I know how. It's galvanizing of steel is not an alternative, and please don't ever think of it as an alternative to good site practice. It should complement good site practice. It's for those inevitable instances that the cover concrete is deficient in some way. The contractor doesn't get the required cover, or there's a lift which is a weak link in the chain, or there's some blowholes. It's those things that we're guarding against. We're not using it as an excuse for the contractor not to be diligent with good site practice and good concrete practice. So just to leave you, this is a poem that was given to me by my late friend, John Lane. And I'll just read a couple of parts of it, and you can read the rest sometime in your own time. It says, but engineers should welcome cracks, for in diagnosing their cause, they may learn. Maybe some cracks are acceptable. Often our clients are too condemning of some relatively benign cracks. And cracks are often nature's way of putting a joint in where the engineer forgot or didn't think of it. I like this. He says, cracks are so human as they also arise from overstressing. First stress, then strain, then crack up. At the crack, there's no more stress. It's alleviated. It's gone. Only a void. The concentration of stress has moved elsewhere. In human terms, maybe passing the buck. And then he talks all about how we must study the shape and the pattern of the cracks to learn more about them. And it ends off by saying, the problem is not only how to avoid cracks, but to take an enlightened view of their significance when they occur and how to take appropriate action if necessary. So with those thoughts, I will say goodbye and invite any questions that might be.
Thank you, Rod. Thank you so much for sharing this with us in such a practical way. Just in terms of time constraints, we've had a couple of chats on a couple of questions on chat. I'm going to pose those to you, but we're not actually going to be taking any questions from the audience today. So Rod, if I can just read, let me just get to those questions. We had a question. What is the best way to reinforce re-entrant corners against dry and shrinkage? How much steel and at what position within the thickness is the most effective?
Yeah, that's a very good question. I would always put more than one bar in a corner with re-entrant, or in a re-entrant corner, and I would put one bar close to the surface. If it's an industrial floor, you really want to reinforce fairly close to the surface, sort of 30-40 millimeters from the surface. And I would put something like at least a Y10 bar. Use Y10 bars at least. But what works very well is to take some offcuts of mesh and put those across the corner so that the principal bars in the mesh run perpendicular to where you would expect the crack trajectory to run. And then I would always reinforce the entire panel adjacent to the re-entrant corner.
Thank you, Rod. Another question, how do you then reduce or eliminate the corrosion cracking of reinforcing steel? And I think you've addressed that to some extent by saying hot dip galvanizing. Coupled with that, if using galvanized steel with plain steel, there may be bimetallic corrosion.
Yes, that's a good point. Can I answer that one first?
Yes, please.
Yeah, bimetallic corrosion, the combination of the metals, the plain bars will cause the galvanizing to be consumed a little bit more quickly. But the amount of zinc that they put on a galvanized bar is quite generous, and it works. You don't have to worry too much about that. You can even combine stainless steel with mild steel, or stainless steel with galvanized steel. It just means that whichever steel is more active will rust that little bit more quickly, but generally only in proximity to the point of contact where it makes electrical contact. But far better to do it and mix the steels than to not do anything. So don't let that stop you.
Right, and then the comment, is there a reference which states a recommendation in concrete cover reduction if the steel is galvanized, meaning paying for some more galvanizing, allowing for a saving in concrete in cover reduction? I don't know if you can comment on that.
Yeah, you might reduce the cover slightly, but I'm hesitant to say do that, because I know from experience that if you specify 50 millimeter cover, in a lot of places you end up with 20 or 30 millimeter cover. And if you now say, well, because it's galvanized, we'll relax the cover to only 30 millimeters, you might end up with no cover. So I would think very carefully about it, and I don't want to offer a blanket recommendation. I would just say each engineer must make a judgment call based on the specific merits of that project. But just something I forgot to mention, a question before the previous question was, how do we stop reinforcement corrosion? And one of the best ways is to not use reinforcing. I used to teach concrete technology when I worked at the Concrete Institute, and I used to put up a slide of the Pantheon in Rome, a 2,000-year-old concrete structure which stands today and remains serviceable today. And I used to make the point to the students that if there was reinforcing steel in that structure, it probably would not be standing today, because the reinforcing would certainly have lost its passivity in the time and rusted and caused all these problems that we talk about today. And there's many applications where engineers put reinforcing steel where they don't need. And one of the best examples of a successful structure with no reinforcing steel is the wind block. The architect based in Port Elizabeth, Al Stratford, invented the wind block, and it's an incredibly successful window frame because it has no reinforcing steel in it. It doesn't need reinforcing, and it works much better because it doesn't have reinforcing. If they had reinforcing in, they would be a disaster. And if you have to put reinforcing in a thin section like a wind block window frame or a precast wall, use galvanized or stainless steel or one of the alternatives. We now have basalt fiber and fiberglass rods and things that don't rust. Consider one of those alternatives rather than steel.
Thank you. And incidentally, in the current issue, the March issue of Concrete Baton, which is available on the website, there's actually an article on the Pantheon Dome. It's under the heading Iconic Concrete. Go and read about that. Rod, just the last question. What is the specified film thickness for galvanizing?
That's an interesting one. There's a standard that you must specify for galvanizing. It's SANS 121, ISO 1461. And it gives you a minimum zinc thickness of 75 microns. But inevitably, when you galvanize rebar, you get far more than that. So it's contained in the standard. You don't have to specify it yourself, but I would always recommend that you specify the hot dip galvanizing standard, SANS 121, ISO 1461. That's the one to specify.
Okay. Rod, the very last comment or question. What are your thoughts on reinforced concrete structures, walkways, or balconies that are not waterproof and only tile? Are there codes specifying that these elements must be waterproofed?
Yes, yeah, I don't think there's a mandatory requirement to waterproof them in terms of South African building standards, but they usually are needed to be waterproofed, and architects usually do specify waterproofing because they don't want water coming through the soffit and staining the soffit. And it's a very difficult thing to get right, Hanley, because you've got one chance. If you waterproof before you put tiles down, and there's any defect in that waterproofing, you inevitably get leakage of water in the future. It's a big, big problem where people put these green planters on the roofs of buildings or above car parks, parkades. And the waterproofing membrane makes it difficult to lay the tiles. And what you find is that when you try to combine all these things and satisfy all the standards, you inevitably violate some rules in some standards. The waterproofing standard requires a minimum slope of 1 in 50, and the Part L of SANS 10400, that's roofs of the building regulations, requires a minimum slope of 1 in 80, and very often those two requirements are violated. The structural engineer says, no, you can't put that weight of screed on top of my slab, and the architect puts less, and then you get the problem of ponding, which makes the waterproofing failure even more severe. So my advice is, if you can stay away from balconies that need to be waterproofed, do so. Not a good idea. Rather put a roof over the balcony and try not to have to waterproof them at all.
Rod, thank you so much. And everybody who stayed online, thank you. Rod, we had a host of comments in the chat to say thank you for a great presentation. Thank you for a very informative presentation. And I just want to endorse this. We had a record number of attendees to our Concrete Fix today. And as I mentioned earlier, Rod, either you are the draw card or your subject is the draw card. We'll have to take a bet on that one. But
Yeah.
be it as it may, thank you for sharing with us today. And then just a comment from Natasha. Many people logged on with a name like Office or Samsung and that. Please, Natasha cannot get the attendance register correct and know when you need CPD points, if that is how you log on. Please let her know that you attended the session today to make sure that you can get your CPD points. Rod, thank you. We appreciate you sharing with us today. Remember to buy Fulton's Concrete Technology if you haven't done so already, the 10th edition. There's the whole chapter on cracks and cracking that Rod has written. Read more about it. Thank you, everybody. Stay safe and go well. Thanks again, Rod.
You're welcome, Hanley.